Hey everyone, and welcome. If you're deep in multivariable calculus, you've probably hit that moment where describing a really simple 3D shape feels, well, way too complicated. Today, we're going to pull back the curtain on a tool that makes all that complexity just melt away: cylindrical coordinates. So let's dive in and see how they work. I mean, just think about it. Try describing a simple soda can. In our standard XYZ world, you're stuck with this clunky equation: x squared plus y squared equals some constant. Yeah, it works, but it feels so unnatural, right? The coordinates just don't fit the shape. There has to be a better way. And of course there is. For anything with that round, circular symmetry, we're talking pipes, columns, that soda can, we have a system that is so much more elegant. And this isn't just about making equations look prettier. Trust me, when you get to triple integrals, this way of thinking is an absolute game changer. It makes calculating tricky volumes so much easier. And that system is, you guessed it, cylindrical coordinates. So instead of finding a point by going some distance on x, then y, then z, we're going to find it in a totally new way. We'll think about its distance from the center, its angle of rotation, and then its height. It's a whole different map for 3D space. Now, if you're getting a little déjà vu, thinking, hey, this sounds kind of familiar, you are spot on. The absolute best way to wrap your head around this is to realize it's just the 2D polar coordinate system that you already know and love, but we've just bolted on a z-axis for height. It's really that straightforward. So let's break down the three parts. First up is r. That's your radial distance out from the z-axis. Then you have theta, or theta, which is just that angle you rotate around in the flat xy plane, exactly like in polar coordinates. And z? Well, that's the easy part. It's the exact same z we've always used for height. No changes there.
Okay, so this new system is great, but to really make it useful, we need to be able to talk to our old system, Cartesian coordinates. We've got to be able to translate between the two. So let's build our conversion toolkit.
These formulas are really just your basic trigonometry in disguise. To go from cylindrical to Cartesian, you just find x with r cosine theta and y with r sine theta. And to go the other way, it's just good old Pythagorean theorem. R squared is x squared plus y squared. And the best part? Look at z. In both directions, z just stays z. It's like our anchor between the two worlds. And here is the payoff. This is why we do it. Look how clean and simple these equations become. That messy x squared plus y squared equals c squared for a cylinder, it just becomes r equals c. Done. A cone, which is a pretty weird equation in Cartesian, simplifies all the way down to z equals r. It is just incredibly efficient. All right, theory is one thing, but let's actually get our hands dirty and see how this works. We're going to walk through a couple of examples, starting with a simple point and working our way up to entire surfaces. Let's start with level 1, the most fundamental skill, just taking a single point in cylindrical coordinates and finding its home address back in the Cartesian system. So let's take the point 4, 2 pi over 3, negative 2. We literally just grab our conversion formulas and plug everything in. For x, we need r times cosine of theta, so that's 4 times the cosine of 2 pi over 3, which gets us negative 2. For y, it's r times sine of theta, or 4 times the sine of 2 pi over 3, which is 2 times the square root of 3. And z? Well, z is just z, so it stays negative 2. And there you have it. Our final point is negative 2, 2 root 3, negative 2. It's a straight plug and play. Okay, let's level up. This time, instead of just a point, we're going to take a whole equation written in cylindrical coordinates and figure out what 3D shape it's actually describing. Okay, check out this equation. R squared plus z squared equals 100. The magic key to unlocking this is our absolute favorite conversion identity. We know that r squared is just a stand-in for x squared plus y squared. So let's just swap it out. And instantly, the equation becomes x squared plus y squared plus z squared equals 100. And hey, we all know that one. That's a perfect sphere right at the origin with a radius of 10. How cool is that? Okay, pause for a second because this is a super important point. This is a classic trap students fall into. You see the letter r in an equation, and your brain immediately screams cylinder. But you have to look at the whole equation. That little plus z squared term completely changed the game. It was the crucial clue that turned a potential cylinder into a sphere. So always check the context. All right, you ready for the final challenge? For our last example, we're going to convert an equation that needs a little algebraic massaging before we can figure out what shape it is. Here we go. The equation is z equals 2r. Now, our key identity involves r squared, not plain old r. So what do? Simple algebra trick. Let's just square both sides of the equation. That gives us z squared equals 4r squared. And now we can make our substitution. We swap in x squared plus y squared for the r squared, and our final equation becomes z squared equals 4 times the quantity x squared plus y squared, which we should recognize as the equation for a cone. So after all of that, what are the absolute most important things you need to walk away with? Let's boil it all down to the essentials. Here's your cheat sheet. First, the big idea: always just think polar coordinates plus a z for height. The formula you will use over and over and over again is r squared equals x squared plus y squared. Know your basic shapes. R equals a constant is a cylinder. Z equals r is a cone. And the biggest rule of all, context is everything. Always look at the entire equation before you decide what shape you're dealing with.
And that brings us to one last little thought. We described a sphere today, but using r squared plus z squared equals 100 still felt a little clunky. It makes you wonder, right? If cylindrical coordinates are perfect for cylinders, is there maybe an even better system out there that's designed specifically for spheres? I'll leave you to think on that. Thanks for tuning in.